Okay, let's start. Hello everyone, my name is Jie Zhang from KAIST. Today I will talk about our work ZnG, which is architecting GPU with new flash for scalable data analysis. Firstly, I will use a single slide to summarize this work. This work mainly focused on the issues of using GPU to process large-scale applications. Traditional computer systems usually employs GPU and storage as discrete device. The application's dataset initially received in the SSD but should be processed in the GPU. Transferring the data from SSD to GPU need to go through multiple software stacks and hardware boundaries. These steps become the performance bottleneck. To address this, we propose ZnG. It moves the SSD close to GPU cores and can deliver high SSD bandwidth. Our evaluation results show that ZnG can improve the performance by 7.5 times compared to the prior work. I will continue the presentation with the motivation and the challenge. The data in the world is increasing at amazing speed. Here's the examples. In 1 minute, millions of messages, emails, and Twitters are generated in the internet. If we sum up the data from all sources, the total amount of data has increased by 40 times since 2010. To process such large amount of data, we need to have a high-performance hardware for acceleration. Graphic processing unit, also known as GPU, can be a good candidate. We choose GPU because GPU is a scalable hardware which can integrate thousands of cores. As you can see from the figure, GPU's performance has dramatically increased during the past 10 years. By 2016, the performance of GPU has exceeded that of the CPU by 6 times. As GPU employs an SIMT architecture, it also can exhibit a promising energy efficiency. NVIDIA GPU has proved its energy efficiency in Green 500 rank. While the computing power of GPU is increasing, the memory technology lags behind a lot. Firstly, the memory capacity is not scalable. Secondly, the memory device is power hungry. For example, single DRAM package has at most 4 GB capacity and it consumes up to 5 watts per gigabyte. As a comparison, the new storage median ZNAND can increase the memory density by 64 times and reduce the power consumption by 25 times. So compared to DRAM, ZNAND is a better candidate to store large data sets. Since GPU memory has limited capacity, we can place the data in ZNAND-based SSD we call ZSSD. Unfortunately, GPU cannot directly access data from ZSSD due to the physical boundary and the software constraints. So traditional heterogeneous system employs a host-side memory to buffer the data from ZSSD. As ZSSD and the GPU use different software stack, the host CPU also needs to copy the data from the kernel space to the user space. Afterwards, it transfers data to the GPU side memory over a GPU software stack. Once the data is ready in the GPU side memory, GPU is able to access the data. However, the data movement between the GPU and the ZSSD can introduce huge overhead. We break down the total execution time of evaluated workload into a storage access time, data transfer time among SSD, the host, and the GPU processing time. As you can see from the figure, the average data transfer time accounts for 71% of total execution times in our evaluated workloads. To eliminate the data movement overheads, prior work proposed a hybrid GPU. It replaced the GPU side memory with ZSSD. GPU can directly access ZSSD through a customized interface. With the hybrid GPU design, the GPU can leverage the high storage capacity to accommodate all the datasets. It can reduce the power consumed by the GPU DRAM, and it also can eliminate the redundant data copy. However, there's a huge performance disparities between the GPU and the ZSSD. For example, the GPU cores can deliver tens of the teraflops throughputs, while ZSSD can only serve a few gigabyte data in 1 second. The limited bandwidth of ZSSD becomes a performance bottleneck in the hybrid GPU system. To better understand the performance disparity, I will firstly show the internal of traditional GPU design. Traditional GPU consists of a group of computing units called a string multiprocessor, also known as GPU-SM. It also employs a memory management unit and a couple of L2 cache and DRAM controllers. The GPU-SM MMU L2 cache, and the DRAM controllers are connected through the interconnect network. Within the SM, the instructions are executed with a typical pipeline, including the fetch, decode, execution, and retire. The SM also employs a private L1D cache to serve the load store instructions. The GPU enables memory virtualization by employing TLB and memory management units. Before the memory requests to access L1D cache, they need to look up the TLB for address translation. If there's a TLB miss, the memory management unit will perform the address translation. The 1,000 cores in the GPU SM can deliver more than 10 teraflops in total. To match with such high throughputs, GPU usually construct a high-performance L2 cache bank and the memory controllers. The shared L2 cache provide a few terabyte throughputs, while the memory controllers can deliver hundreds of gigabytes per second throughputs. While the memory system in the traditional GPU can provide hundreds of gigabytes per second throughputs, the hybrid GPU performs much worse. This is because the hybrid design replaces the memory systems with an SSD. Specifically, within the SSD, a request dispatcher is employed to dispatch the memory request packets from the GPU network. An SSD controller is used to perform the flash firmware, such as FTL. The FTL translates the logical address of the incoming memory request to the flash physical address. It also performs garbage collection and well leveling for the underlying ZNAND packages. The SSD includes an external DRAM buffer. The DRAM buffer consists of low-power DRAM packages whose capacity ranges from 512 MB to 2 GB. The DRAM buffer stores the metadata for the address translation, such as a page mapping table. It also buffers the flash pages for the read-write request. The SSD also employs multiple flash controllers to manage the I/O transaction of the underlying ZNAND package. The flash controller and the ZNAND package communicate through the flash channels. The flash channel is a thin bus structured network with 8-bit links, which is running at a low frequency. We analyze the performance of each component in the SSD. Since the hybrid GPU only employs a single DRAM buffer, it only can provide 11.2 GB throughput. The flash channel is initially designed for the slow device, so 8 flash channels can deliver only 25.6 GB per second bandwidth in total. Interestingly, if we can fully parallelize the request across different ZNAND packages, the ZNAND read bandwidth can be as high as 340 GB per second, which much exceeds the performance of DRAM buffer. Due to the long ZNAND write latency, the ZNAND write bandwidth is just as low as 10 GB. The SSD controller usually employs 1, 2, 3 low-power cores to perform the address translation, so it can only process 4.8 GB data per second. We also measure the performance of the network interface in the SSD. A single request dispatcher is not sufficient to serve all the requests from multiple L2 cache banks. Compared to multiple memory controllers, a single request dispatcher can increase the latency by around 5 times. Based on the performance analysis, we can conclude that traditional SSD architecture actually constrains the potential performance of the SSD. To narrow down the performance disparity between the GPU and SSD, we need to rethink the GPU SSD architecture. So we propose ZnG, which is a new GPU SSD architecture. ZnG can maximize the GPU memory capacity by fully replacing the GPU internal DRAM with ZNAND packages. It also can significantly improve the SSD performance. Considering the flash channel and the network interface can constrain the performance of ZNAND, we designed an architecture to directly expose the ZNAND to the GPU. The poor FTL performance is because of the limited computation power of the SSD controller. To address this, we automate the FTL functions in the existing GPU hardware to achieve zero overhead address translation. As the DRAM buffer performance worsens ZNAND, we remove the DRAM buffer. Instead, we leverage the high-performance L2 cache and the flash internal registers as buffers to improve the utilization of the ZNAND bandwidth. Next, I will talk about our architecture designs to address the performance bottleneck. Our key idea is to expose a high-performance ZNAND to the GPU. The traditional flash channels is not sufficient to expose the full throughput of ZNAND. To address this, we replace the traditional flash channel with a high-performance flash network. The new flash network is built from mesh network, which enables the flash controller to access any ZNAND packages. We expand the link width to 64 bits. It is 8 times of the traditional flash channel. Since the DRAM buffer performs much worse than ZNAND, we detach the DRAM buffer from the SSD data path. Instead, we will make the GPU directly access data from the ZNAND. We also need to remove the performance bottleneck caused by the GPU network interface and the FTL. In our design, the SSD controller is detached from the SSD. We directly attach the flash controllers to the GPU network. As the L2 cache bag can communicate with any of the flash controllers, this design can improve the network parallelism. We integrate the request dispatcher in each flash controller to interact with the GPU network. The FTL performance is limited by the computing power of the SSD controller. Our key idea is to leverage the GPU high-performance hardware to automate the FTL functions. We observe that the memory management unit translates the virtual address of the memory request to the logical address. The FTL will continue to translate the logical address to the flash physical address. So we consider to integrate the FTL in the memory management units. The memory management units can directly translate the virtual address to the flash physical address. However, it is challenging for the integrations. There are several reasons. Firstly, the FTL needs to update the mapping information for each write operation. The metadata update in MMU can result in frequent TLB shutdown. Secondly, the FTL requires computing power to execute complex algorithms for the garbage collection and well leveling. Unfortunately, the MMU cannot provide such computing power. Lastly, the FTL needs huge space to store the mapping information. The MMU internal buffer is not sufficient to accommodate the mapping information. The FTL maintains a page mapping table to store the mapping information of each page. So the mapping table can cost a high memory space. For example, 1 terabyte SSD needs 1 gigabyte memory space to store the page mapping table. To reduce the memory consumptions, we adopt a block mapping table, which only stores the address mapping information of large data blocks. The new mapping table only consumes around 100 kilobyte memory space, which can be stored in the MMU's internal buffer. The MMU will translate the virtual block number of the incoming memory request to the flash physical block number. We also observe that most data analysis applications are read intensive. As you can see from the figure, more than 90% of the memory access are read in the evaluated work. We can make the MMU to serve the reader request. The reader request won't change the block mapping table, so it does not introduce TLB shutdown. For the remaining write request, we will manage the page mapping information and the data separate from the read request. Specifically, we'll employ a programmable row decoder in the ZNAND. We can program the page mapping information in the programmable decoder. For the incoming memory request, the row decoder can redirect the request to access the target flash page. We also allocate log blocks to store the updated data. The log blocks are different from the data blocks which are recorded in the memory management units. In addition to the new design of MMU and the ZNAND, we also create a helper thread to manage the ZNAND blocks. For example, when the log blocks are fully programmed, the helper threads will merge the page mapping information to the block mapping table in the MMU. Afterwards, it will migrate the data stored in the log blocks and erase the log blocks. The helper threads also perform garbage collection and well leveling. We detach the DRAM buffer from the ZSSD due to its low bandwidth. However, simply removing the DRAM buffer can result in the poor performance. We configure 2 sets of ZSSD, one employ a DRAM buffer and another remove the DRAM buffer. We compare their performance. As you can see from the figure, removing the DRAM buffer can degrade the performance by up to 63 times. One reason is that the GPU memory access granularity is 128 byte, while the minimum access granularity of ZNAND is 4K byte. Accessing the 128 byte data from the ZNAND wastes the bandwidth to transfer the unused data. Although we also evaluate that the GPU application re-access data from the same pages for multiple times, but unfortunately, the SSD cannot buffer the data for faster access, so it cannot utilize such special locality. Our another evaluation shows that the small number of ZNAND pages experienced intensive writes. As ZNAND write latency is much longer than ZNAND read latency, so intensive writes can block the flash array and reduce the total throughput. To address the performance degradations, we utilize the GPU L2 cache to buffer the whole flash pages for read request. While the GPU L2 cache can provide the high throughput, it unfortunately has very limited capacity. We increase the L2 cache capacity by employing the emerging non-volatile memory STM-RAM. STM-RAM can increase the capacity by 4 times. To maximize the utilization of the L2 cache, we speculate the spatial locality of the fetch data and dynamically adjust the data access granularity. We revise the L2 cache banks with new hardware. In addition to the existing cache array, we design a prediction table and an access monitor. An incoming read request will search its target data in the L2 cache array. If missed, the request will access the data from the underlying ZNANDs. In parallel, the prediction table speculates the spatial locality of the target data and arbitrate whether to perform the data prefetch. The access monitor adjusts the data prefetch granularity based on the cache line utilization in the L2 cache. One thing to mention is that it is not beneficial to accommodate the write request in STM-RAM. This is because the STM-RAM suffers from its long write latency. To address this, we buffer the dirty data in the flash internal registers for write request. The flash register can merge the small write requests before programming them in the ZNAND arrays. However, the problem is the ZNAND array contains the flash register to store only 2 flash pages. We propose to increase the number of flash registers to shelter as many write requests as possible. We design a shared data path between the ZNAND array and any flash register to enable direct communication between each other. To maximize the flash register utilization, we group the flash register across all ZNAND arrays within the same die to serve as a fully associative cache. In this design, data can be placed anywhere within the flash register. To achieve this, we employ a simple interconnect network within the ZNAND dies. Next, I will talk about the evaluation. We set up our experiment based on a Maxim Simple SSD simulator. For the GPU, we adopt an NVIDIA GTX 580 models. For the SSD, we choose Samsung 500 GB Z SSD. The key parameters are listed in the table. We also configure 5 different system configurations. Hybrid GPU is the GPU SSD architecture we mentioned before. ZnG base is the baseline architecture of ZnG, which does not adopt the flash bandwidth optimization. ZnG read OPT is a ZnG base with our L2 cache design. ZnG write OPT is ZnG base with our flash register design. And then lastly, ZnG is ZnG with both L2 cache and the flash register designs. We compare the ZnG access bandwidth of different system configurations. As you can see from the figure, hybrid GPU only achieve 4.2 GB per second. This is because of the limited flash channel bandwidth and FTL performance. ZnG-based performance even worse than the hybrid GPU. The access granularity of ZNAND is totally different from that of the memory request, so only a few flash array bandwidth is utilized by the request. ZnG read OPT improved the bandwidth by efficiently serve the read request, but its performance is constrained by the long write latency. In contrast, the ZnG write OPT can significantly reduce the number of flash writes, so it can hide the penalty of the long write latency. Lastly, ZnG optimizes both read and write bandwidth, so it can achieve the best performance. We also prepared 10 different evaluation results. If you are interested in, please find them in the paper. I will complete the presentation with conclusion. Processing explosively increased data size require heavy usage of GPU accelerators. However, the long data paths between the storage and the GPUs cause huge performance overheads. We propose ZnG. It integrates the SSD into the GPU to maximize the memory capacity and achieve high performance. Our evaluation results shows that ZnG can improve the performance by 7.5 times compared to the prior work. Thank you very much for your attendance.